last time we were talking about some of the algebra that we need to deal with in talking about this phenomenon of squeezing. And so the key operation we have is the unitary transformation that we call the squeezing operator. It has this form. Okay? Well, maybe get to today, if not next week, sort of where this comes from physically. Obviously, it involves something with pairs of photons, because it has A squares and A daggers, A dagger squares. And so we'll talk about that perhaps a little bit later in this lecture. So the state that one obtains, the state of a single mode harmonic oscillator that is obtained by operating the ground state of the harmonic oscillator by the squeezing operator, is what we call squeezed vacuum. Okay? And we draw it here in terms of the quadrature picture. It is a state that has zero mean amplitude, and it has fluctuations along the different quadratures that are anisotropic, that are squeezed along one of the quadratures. Actually, this is drawn backwards. Sorry. It's supposed to, let me try that again. So here's the X quadrature associated with that, and this is the P quadrature, and this is that state. So it's reduced uncertainty along the X quadrature and increased uncertainty along the P quadrature with respect to that theta. Okay? Obviously, there is a squeezed vacuum state of the kind I thought I drew, but it would have the squeezing parameter with a different phase. So that this squeezing parameter, as written here, this is not a square. The square is supposed to be over there. Is a complex number whose magnitude determines the amount of squeezing and whose phase determines the quadrature along which you are squeezed. And there's this factor of 2 that floats around over there. So it's half the argument of this, that is the quadrature along which you're squeezed. Okay? And this state is a minimum uncertainty state. Another important algebraic relationship is that this squeezing transformation, this unitary operator, induces a unitary transformation that's known as the Bogoliubov transformation. Okay? It kind of mixes together A and A dagger. So it's kind of like a rotation between A and A dagger by an imaginary angle. And there's an algebraic relation. You may remember there's this weird thing about Lorentz transformations and imaginary angles and their group relationships. So there is this kind of group theoretical relationship between the Bogoliubov transformations and the group SU11, if you care. So anyway, but the idea here is that this Bogoliubov transformation, because of this mixing between A and A dagger, what it does is it rescales X and P along some direction. Okay? Associated with that squeezing parameter space. Furthermore, what we saw last time was that one way to understand where the squeezing was coming from was the fact that there is a coherent superposition of the vacuum state with the state that has a pair of photons in it, 2 photons in it. And the phase of this complex amplitude determines the quadrature along which I'm squeezed, where I get destructive interference versus constructive interference. Okay? So something which we say, is kind of related to the continuous variable reduction of some quantum uncertainty, it has to do with this kind of coherence between different numbers of photons. And in this case, it's between something with 2 photons and something with the vacuum. Okay? And generally speaking, this state has only even numbers of photons in it. You can kind of see that because if you were to act this operator on the vacuum, expand it out, it only has even powers of a dagger in there. And one of your homework problems is to derive this, or something close to it. All right? Right. One last thing about this that I think I failed to mention last lecture is that we can define for example, not just a squeezed vacuum, but we could have a squeezed coherent state with some mean amplitude alpha and some squeezing that need not be squeezed along the same direction as this phase. So it could have, some arbitrary kind of picture like this. Okay, so this is what we call a squeezed coherent state, and it's specified by the mean field and the squeezing amount. And it's just obtained by displacing through the phase-space displacement operator that we have discussed, the squeezed vacuum. Yeah?
Does it make any difference which way around you do the...
It does. That's exactly what I was about to say. This is not the same thing as they don't commute. You find a different amount of squeezing in this case. And this is the way that, to me, it makes sense in most sort of modern texts define squeeze coherent states, or this way. It was originally defined, there was a kind of debate at like what's the right, 20 years ago or more, how to do it, but we're not, these aren't equal, so this is, because this has the same amount of squeezing as the vacuum, squeezed vacuum would have had. It makes more sense to me to define it that way.
If you do it the other way, do you still get a squeezed coherent state?
You do.
Okay.
But the amount of what you're doing is you're squeezing also the X and P, so you'll change.
Yeah.
What you'll do is you'll shrink and increase your coherent amplitude. So
Okay.
your coherence that you get is not that alpha. You'll have a different alpha. You see that? Because you're going to end up de-amplifying and amplifying it. So it is a squeezed coherent state, but with a different alpha. So why would we do it that way? All right. Now, what we were talking about at the end of the lecture was the way in which one detects a squeeze state, and that will sort of lead us into the question of what the heck is a squeeze state good for? So we were talking about, in order to detect a squeezed state, we need to somehow measure in some phase-dependent way what these fluctuations are, because they vary as a function of the phase. So we need some kind of phase-sensitive detection. Now, one thing we discussed that, just to remind you, we talked about this notion of shot noise. Right? So if I have a photodetector, and it's an ideal photodetector, which has perfect quantum efficiency, that's the jargon for saying that every photon that comes in is converted to a photoelectron. Then if there's any fluctuation that we would see in the signal, that the photo signal that we get, would come from the fluctuations of the input. Okay? And if there are, if this is not, there's no technical noise, no thermal noise, then all of those fluctuations would be due to quantum fluctuations in the input field. And that's that's the part of the shot noise that we are caring about right now. And so what we said is that if we had a situation where, I had just for example, if I had a coherent state, and if that coherent state had an amplitude that was very small compared to 1, and when I looked at that, what I would see is, every once in a while I get a photon. Most of the time I get nothing. Every few times I might get 2. And this is kind of photon counting. And this is what we call the kind of Geiger mode of the photodetector. And the fluctuation that we see in the number of clicks here would be due to the fact that there is an uncertainty in the number of photons, which, say, for a coherent state, is the square root of the mean number. Okay, those are the Poisson statistics. On the other hand, if we have a situation where alpha is big compared to 1, so that we have many photoelectrons in some interval, it's more, instead of talking about discrete electrons, we talk about a photocurrent. Okay? And in that situation, what one might see, if this was a well-stabilized laser with a very definite intensity, then what we would see on the photodetector, some kind of photocurrent, we looked at this as a function of time, it would have some well-defined mean value and then some fluctuations about the mean. Okay? And those fluctuations about the mean is what we would call shot noise. It's the same physical underpinning. It's due to the fact that there's some randomness in the number of photons that will be measured in any given time interval, because this is not an eigenstate of the number operator. It has an uncertainty in the number of photons. And particular coherent state has as we know, the probability distribution of seeing n photons in a given time interval is equal to a Poisson distribution. And it's a simple exercise, maybe will be assigned, to show that in the limit that the mean number goes to infinity, that this approaches a Gaussian. as I say, when the mean number of photons becomes very large. Why does this feel like I'm writing with wax? Anyway, sorry. Okay, so this distribution looks Gaussian, centered around the mean with the fluctuation that's given by what we expect. Okay, the variance is equal to the mean number. Okay, so a Poisson distribution looks Gaussian. It's really just a central limit theorem. Okay, so another way we solve that, and which I think is interesting, is that if we made, and this I did kind of stumble through this at the end of the last lecture, so let me just repeat it, what I was intending to say. So we talked about the Marlow transformation. You remember that? So this is a way of kind of transforming away the mean field and looking then solely at the fluctuations around the mean. Okay? So under the Marlow transformation, what we're going to do is take the mean field out of the state. So we're going to do a unit, it's like a change of picture, like going to the Heisenberg or the interaction picture. We're going to take away, we're going to displace back towards the vacuum, do the inverse transformation. So if this were a coherent state, then if this were a coherent state, then this state would be the vacuum. And put those means into the operators, so that we've displaced the operator instead of the state. So in some sense, this operator now, this is kind of the mean field, and this is the fluctuations. This operator here is telling me something about the fluctuation relative to the mean. Does that make sense to everybody? So with that, if I make in that picture, we're now the state in this new picture, let me define this as psi tilde. Psi tilde has 0 mean. Okay, yeah.
So for each side, there will be a particular
Correct.
alpha.
That's correct.
Which is the mean
Of that side.
value of the side.
Yep. Indeed, that is correct. So this is a picture that we're doing saying we know what the mean field is for that particular state. And that's alpha. And now what I'm going to do is I'm going to displace away that mean value of that particular side and put that into the operator instead. So it is a state-dependent kind of transformation. So but for that particular state, this is then 0. And if I look at the number operator in this new picture, then that is equal to a dagger plus alpha star A plus alpha, which is, well, this goes to this, not that it equals that. Plus the magnitude of alpha e to the I phi minus plus e to the plus I phi. A dagger plus And since we're assuming that under the limit that we're looking at when alpha is very big compared to 1, such that this is a huge number, and the number of excitations in the fluctuation is small, as it would be, for example, for this squeezed vacuum state, then we can neglect this when we look at the average values of this. So this is the continuous variable limit, then my photocurrent, which is given by something having to do with this counting this number, is equal to the intensity plus this variable, which is equal to x5. Okay? So this is the square root of the intensity. So you can see if this were, so this is my number operator. In this limit, if this is a Gaussian random variable, then the photon number statistics will look Gaussian. It has this mean, and this operator is representing the fluctuations around the mean. And if this were something like a squeezed state, or a thermal state, or something like that, then this would represent the fluctuations around that. Where the quadrature that I'm measuring would be equal to the quadrature associated with the phase of the mean. Okay? Because that's where that phase came from, alpha. So what you're measuring, when you're measuring, doing photo counting with a large amplitude coherent state, is essentially what you're measuring is the quadrature fluctuations along the amplitude. You're measuring the amplitude fluctuations along the phase of your phasor. Okay? And if you change that, everything, if you rotated the whole thing, you wouldn't be able to rotate this relative to this. If you just did direct photon counting, no matter how you change the phase, if you put a phase shifter in front of your photodetector, well, that would just rotate the whole thing. You'd measure the same amount of fluctuations. You wouldn't measure different quadratures of your squeezing. So direct photon counting doesn't give you the ability to look at the phase of your fluctuations relative to an arbitrary phase. You need to do something different. And that something different is homodyne detection. So that's what we were talking about, and let's pick that up now. So, as we discussed last lecture, in homodyne detection, the idea is what you have is the signal whose value you want to measure relative to an arbitrary phase. So you have your input signal. And what you do is you mix it, you beat it together on a beam splitter with what's called the local oscillator, which is a complex amplitude with some magnitude and phase. And as we discussed last time, in order to deal with the fact that my local oscillator might have some excess noise, and that excess noise would get reflected and mixed with my signal, we can get rid of that in a balanced scenario. So in the balanced scenario, which is the one that is typically discussed in the context of the most sensitive measurements in quantum optics, you have two detectors, and then you look at the difference in the photocurrents that come out of those two detectors. Okay? And that's my output of the signal I want to measure. So, let us see. Where is what I was just looking at? Just want to get my notation straight here. Okay, so in order to treat this problem in the quantum mechanical context, what we need to remind ourselves is how do we deal with something like a beam splitter in quantum optics? So you remember, I'm sure, from your homework from last semester, you solved that problem. And this is basically, so the beam splitter is an example of a linear transformation on the mode, something we're going to discuss in much more detail later this lecture, hopefully. So the idea is the following. Classically, what happens is I have this beam splitter. If I send in plane waves onto these beam splitters, then, well, I'm going to get some reflection and some transmission. Okay? And this is, we can think about this as a scattering transformation. That's what it is both in terms of the classical waves and quantum waves as well. And we can express this in a kind of Heisenberg picture where we have modes that we'll call the in modes and the out modes. You remember from your studies in quantum mechanics and scattering theory about asymptotic in modes and out modes, right? Maybe you do. But you should have studied that in quantum mechanics. And then the same thing for mode 2. So mode 2 comes in over here, comes out over here. Okay. And what the beam splitter does is there's a unitary transformation that takes, it's a scattering transformation that takes whatever mode into, so the in modes become the out modes. And the out mode is related to the in mode in a linear way. So that's what I mean by a linear transformation. So there's a matrix, which we'll call lambda. So this is out. So the output mode is a linear combination of the input modes. And this matrix, lambda, is just the classical scattering matrix. So classically, we know how the fields transform at a beam splitter. There's a reflection coefficient and a transmission coefficient. And those same coefficients then translate onto the quantum modes. Now we're going to derive that in much more rigorous detail in a moment, but we discussed it a little bit. We had it in homework last semester. So for example, A1 would be out would be the transmitted part of A1 and the reflected part of A2. And the output mode 2 is the transmitted part of mode 1 and the mode 2 and the reflected part of mode 1. Now I'm assuming in my calculation here that this is a symmetric beam splitter, meaning that the transmission reflection coefficients don't depend on whether I come in from this way or from that way. Okay? Now, this matrix here is itself a unitary matrix. It's in this case a 2 by 2 unitary. So lambda here is T, T, R, R. And lambda, dagger lambda, is the identity matrix, which implies that T squared plus R squared is 1, and T R star plus T star R is 0. So if I'm looking at a balance scheme, then this is a 50-50 beam splitter, which means that T squared equals R squared is a half. And since this has to equal 0, we have that T R star is equal to minus T star R. So, for example, we can choose the transmission to be 1 over root 2 and the reflection to be I. That satisfies those conditions. So that tells me that A1 out is equal to 1 over root 2 A1 in plus I A2 in, and A2 out is equal to 1 over root 2 A2 in plus I A1 in. You will so often see a 50-50 beam splitter written in a slightly different way, where it's not symmetric, where, say, the transmission amplitude is a half, and the reflection amplitude is minus, or 1 over root 2, and then this is equal to minus 1 over root 2, okay? It would still, so it would look like this, so the matrix we just looked at was 1, 1, I, over root 2. Alternative, 1 over root 2, 1, 1, 1, minus 1. That's also a 50-50 beam splitter, but it's not symmetric. Okay, you can look at it this way. This is like a rotation by a 90 degrees with a sigma x, and this one's with a sigma y. Because remember, e to the I, sigma times theta is cosine, blah, blah. Anyway, we'll come back to that. It's a little aside there. Yes, sir.
This is kind of a little bit of a tangent type question.
It's a Jacob tangent. We're ready.
Yeah. Okay. Sorry in advance, but I don't know. People talk a lot about like nonlinear optics and stuff like that.
Yes, they do, and we will do that in 10 minutes, maybe. But yeah, go on.
Okay. Well, so it seems like so you emphasize there's a linear transformation there between input creation, annihilation operators, and output. But by quantum mechanics, wouldn't you still have to have a linear process for any even
right. So what the hell is linear and what is nonlinear? What does it mean for something to be nonlinear optics?
So is it that you get basically you move across a different number sector? Okay.
So quantum mechanics is linear, right? Mm-hmm. In that the state space is linear and the transformations on them are linear transformations, such as a unitary transformation. So that's always true. But to say it's linear optics means this. Now I'll explain why that's connected. It's related to the linear response of the medium. That is to say, the medium only responds to one amplitude of the field. If it involved two amplitudes of the field, then we would have a transformation that is not of this form.
Okay.
So for example, the squeezing transformation that we just wrote down is not of this form.
Okay.
It mixed A with a dagger. That can't be done by linear optics.
Okay.
That's one example. It's the sort of the most trivial nonlinear effect. Other nonlinear effects will involve mixing A with higher powers of A dagger. And that's exactly where we're headed.
Okay.
So, not too tangential, right on target. Okay, cool. All right, but we're not quite there yet. We're just discussing here the business of the homodyne detection. So the balanced homodyne detector is one, so what we're going to look at our eye out is the difference between the number of photons coming out of one port and the number of photons coming out of the other port. Okay? So we got to, I'm not going to try to do algebra. I want to make sure I get all my factors right. Yeah, okay. So that is equal to 1 over root 2 so this is A1 in, I have a slightly different notation, but I'm not going to bother with that now. Translate plus I A1 dagger in A2. I just have that root 2 there for some mad reason. Okay. So that's the general transformation. What we're going to do now, as before, we're looking at this scenario where we send in a signal and mode 2 is occupied by something that's got a mean field alpha, okay, something that's like a coherent state. So so my operator here, if I am looking at the state here, again, that whatever we calculate, we're going to take the expectation value where my state has that mean value, then my output signal here, my mode 2, in a coherent state, that's my local oscillator. This output is equal to at least the mean, and then we can look at the fluctuations, will be equal to the signal at the local oscillator phase times the mean alpha. Sorry. Where X in, oh, I'm sorry, that's not. So what I did is I said, I can replace this mode by taking the expectation value by the mean field. And then one of these guys is an alpha star. So it's a dagger. And that gives me that beat node. So in a balanced homodyne detector measures directly the quadrature of the field at the phase of the local oscillator. So let me emphasize that that phase is the phase of the local oscillator. It's not the phase of the signal, it's the phase associated with the local oscillator. And thus, the fluctuations that we measure in the balanced homodyne detector are equal to the fluctuations in the quadrature at the phase plus pi over 2 associated with the signal. All right? So that's the key point. And so, what we see then is the following. If I were to measure, if I looked at the photocurrent difference that comes out of my balanced homodyne detector, what would it look like? Well, what it would look like is the following. If I were to, what we know is that if I were to just plot what these fluctuations are as a function of this phase, then if I have a squeezed state, it will show the following behavior. Those fluctuations will oscillate. Okay, so when I measure, I have to explain to you in a moment what it is I'm actually plotting, what do you measure. But however I measure these fluctuations, as I change the phase of the so-called oscillator, if I were to have some way of adjusting the phase of my laser beam and measuring the noise through a spectrum analyzer of some kind, and I did that as a function of the phase of the local oscillator, I would see it oscillate. And this value here is 1 over root 2, and that is what we call the shot noise level. Sometimes known as the standard quantum limit. And as I vary the phase of the local oscillator, what I'll see is the noise sometimes dip below the vacuum level. So this shot noise, the standard quantum limit, is the vacuum level. And the minimum I would see, if it was a perfect squeeze state, would be e to the minus r over root 2, and the maximum would be e to the plus r over root 2. Okay? So this is when I am aligned, when the phase of my local oscillator is aligned with the semi-minor axis, I get the minimum. And when the phase of my local oscillator is aligned with the semi-major axis, I get the maximum. So what am I actually measuring? So remember, we have this picture here when I sent in a coherent state, which is like the vacuum level. So if I was right here and I looked at what is coming out of my photodetector, my eye out as a function, what I'd find is there's, that noise level that we just kind of so this is the 1 over root 2 level. normalized appropriately, okay? When I then adjust the phase of my local oscillator, what will I see? Well, at some points, like over here, it'll look like this. With the noise reduced below what I had when I had nothing coming in there. And then sometimes at this level, it'll look like this. With a noise level greater than the vacuum level. So let's just think about that a minute, because it's kind of magical and kind of important. What is this level? Well, this is the level I would see if I had nothing coming in, right? If I had nothing coming into this thing, if I had vacuum entering this port, and I looked at, what I would see then is, some of the laser would get reflected, some of it would get transmitted, but because of the fact that there's not a definite number of photons on this thing, I'll see some fluctuations coming in here. And those fluctuations are this. And that's with nothing coming in here. On the other hand, if I put in something, I actually reduce the noise relative to nothing. By putting in squeeze vacuum, I can reduce the fluctuations that I see relative to nothing. And the first person who realized that was our friend Carl Caves, who understood that in an interferometer, somebody just draws this is a problem you're going to do for homework because it's so much fun. Carl, as you may know, got his PhD at Caltech working with Kip Thorne and Kip Thorne's a relativist, and they were working on how would you detect gravity waves. And the way you do that, you try to do that, is by looking at the way in which space-time is stretched when a gravity wave passes through a shift in an interferometer. There's a big interferometer system called LIGO. And so it was a big question mark of, I'm going to try to measure this tiny shift in this interferometer that's coming from this gravity wave that we don't even know is there. And how would we even know if that's systematic noise? And is quantum uncertainty ultimately going to limit the measurements? Boy, if we have any kind of noise in our lasers, it's going to limit what sensitivity I'm going to have in the interferometer. And what was realized is that the problem isn't the quantum fluctuations in here, it's the quantum fluctuations here. The vacuum fluctuations entering the unused port is what makes for the uncertainty in your measurement, your fundamental quantum uncertainty. And instead of putting in vacuum, the idea was to put in squeeze vacuum in the unused port. And that reduces your uncertainty below the standard limit pretty incredible. And it's an interference effect. It's because what you're seeing in an interferometer is that interference. Here it's interference and just in the beating of this signal with this that gives you those effects that I just described. But the more general thing is, the interference of how this ultimately comes back depends on the noise that's entering the unused port. Yeah, Luke.
Is it difficult to make a squeeze state?
Good question. So that's exactly what we're up to now. And the answer is yes, it is. It's difficult to make a good amount of squeezing, and it's taken, that was proposed by Carl in, I don't know, 1980, maybe 1979. Squeezing technology has improved a lot in that time, but not as much as you would have thought. You know, you're probably all born after that point. So it's hard to make a squeeze state, number one. And the other point is that the squeeze state itself, the amount of squeezing you get is fragile. And in particular, if we have loss in the system, if there's any absorption, then that tends to degrade the squeezing. Why is that? Well, what we said is that squeezing had to do with photon pairs. That's something what we're going to discuss. And absorption doesn't just absorb the pairs of photons, it will just randomly absorb one photon or the other. So the correlations between the photons that were kind of at the heart of the squeezing are degraded by loss, any absorption in the system. So it is a challenge. That's why squeezing has never really been like the boon toward low noise communications that everyone, you know, when I was a graduate student, every parallel session, the meeting was about squeeze states. You know, this was in the late 80s, early 90s. But it's never panned out, really. On the other hand, right now, they've beaten down all the, at LIGO, they've beaten down all the noise sources to the point where this matters. The systematic noise, it's really the fundamental quantum uncertainty that limits the ability for LIGO to detect gravity waves. And they're now implementing this in the latest iteration.
So do you know, in a squeeze state that they use at LIGO, what would be the R?
It's a good question. I don't know for sure, but I think typically, typically what one has is about 10 dB of squeezing. So dB, of course, is base 10, and I think that corresponds to an R of about 1.2. R is typically small compared to 1. To get to R of order 1 is a challenge.
You can't have like
No, that's for sure. Can't do that. But maybe, I don't know if we can get, yeah, I don't know what. Ultimately, it's a question, and that's what we're going to discuss now, about nonlinearity and having strong nonlinear processes that are not very noisy or lossy. So let's talk about that.
I've got a quick question
Yes, please.
about this.
Yeah.
So in a lot of the papers that talk about squeezing, you see frequency dependence of
Yes.
the squeezing.
Right.
Is there anything that we can see about that here, or is that just a technical issue with the other types of noise and electronic noise? in the
Yeah,
system?
okay, so there's a whole series of points there. Many things that I swept under the rug, some of which because I didn't want to talk about, and some of which because I don't really know about. So right now, I'm talking about narrow band squeezing, which means that I'm assuming squeezing at a particular frequency, because I've talked only about a single mode. And so that is reflected in the fact that my local oscillator has a certain frequency, which is chosen to be the frequency of the signal. Now, how much squeezing you get at different frequencies depends on, as we'll discuss a little bit now, how the nonlinear response in the medium varies at different frequencies. So to get very broadband squeezing is a challenge. To measure it would involve, you have to think carefully about whether you're, and this is the stuff that, it's outside of my theorist domain, about how you deal with the signal is broadband versus narrowband and what you measure differently. So this noise that we're seeing here has nothing to do per se in my chalky presentation of it here. It has nothing to do with the spectrum of the squeezing. This has to do with the fact that this is vacuum noise. So, in principle, this would be a Wiener process. This would be a Gaussian white noise. There would be no correlation. So in any interval, if I ran this, at some time here, I got this signal. If I ran this thing over and over again, what I'd find is different values, and they would be Gaussian distributed. But there's no correlation from time to time. So this is what's often, we'll talk about this more later in the semester, I hope. This is what's called Gaussian white noise. It's Gaussian because the distribution of possible amplitudes is Gaussian distributed, and it's white because it has an infinite spectrum. But that's not the spectrum of the squeezing. That's the fact that this is, a vacuum fluctuation, and that's infinite bandwidth. Of course, you never see white noise because your detector can't respond to infinite frequencies. So that Now, there's another point you made, which is of course sort of a separate point, which is about technical noise. And so I assumed here that this was an ideal detector with unit quantum efficiency and so forth. But of course that's not the case. And where you operate, so there's going to, you want to convince somebody, including yourself, and that what you're seeing is noise below the vacuum level. You have to say that this noise is not technical noise. It's not like I'm reducing the technical noise in my detector. And again, that's a little bit outside my pay grade, but there are regimes in which these detectors respond very well and regimes where they don't. And you gotta, you're working in the lab, you gotta kind of know how to work that. But one of the ways that we see that is the scaling. You see, the point here is that the fluctuations, if what you're seeing is due to shot noise, then your noise should go like the square root of the intensity. If your noise is growing like the intensity, that's technical noise, because every photon is another noise. If it's really due to shot noise, you go like the square root of the intensity. So that would be kind of one of the tests that we would need to do.
So did I understand it right that all the frequency content for every frequency of the white noise, it's all squeezed the same amount?
That's right. I mean, this is what I want to say here. Again, I'm assuming when I'm saying that I'm looking at squeezing at a particular frequency. Okay, so this is narrow band. One shouldn't confuse the band over which I'm doing squeezing with the frequency content of this signal. That's something else. That, in order to see squeezing at different frequencies, you have to vary the frequency of the local oscillator. All right. Okie dokie. Very good. All right, well, let us then switch gears a little bit to talk about the question of that we want to lead into, which is, where does non-classical light come from? How do we make squeeze states and other kinds of non-classical states? So let's remind ourselves again of what we mean by that. introduction of nonclassical light. So, as we led off the very beginning of the academic year, we talked about lights. We want to really return to the question of light matter interaction, right? Light is coming from radiated by matter. So what we discuss is that natural light that say comes from stars or lamps, fire, bug, is what we would call thermal light. And the state, the quantum state of natural light would typically be, uncorrelated set of modes. So for each mode, we have some tensor product over all the modes, so this, where the state for each mode is a thermal distribution, which is described by a Bose-Einstein distribution. In photon number, or equivalently represented as having Gaussian noise of different coherent states. And that's classical light, right? Now, if we try to engineer, make our machines, the first thing we try to do is make more stable coherent sources. Like radio waves, microwaves, and ultimately lasers. And all of those things, if we have very well defined, are defined by coherent states. Now, what we've said, and I want to just review here, is that the coherent state, quantum mechanically, so this arises from classical current. Why the laser is a coherent state is a more complicated question. The quantum theory of the laser is something we're not going to study, but you can read about it in lots of the books. But for the moment, we'll just take it on faith that for all intents and purposes, the laser is also like a classical current source at optical frequencies. So, why do I say that this is the case? Well, let's look at the fundamental Hamiltonian. So the fundamental interaction is the interaction between the current associated with the charges and the vector potential. That's what you get on field theory. So this is the vector potential of the electromagnetic field, and this is the current operator, represents the momentum of all the charges. Of course, if we're looking at non-relativistic charges and we have some charge distribution, then we can make a multiple expansion. And it's natural for us to think about the dipole distribution as the dominant source of radiation. So we can rewrite this in terms of the polarization current from, E and M, the derivative of the polarization density is the polarization current. This is over CA, which is a minus P dot E type distribution. Okay? And if I look at this, right, so let's just say, we're going to make everything time dependent. This is, say, in a Heisenberg picture or in a interaction picture, generally some time-dependent operators. So we know, so E can be expanded in our usual kind of box quantization of modes. So let's look at the interaction picture. This is the free field. And my dipole polarization density this is the sum over all the dipoles at position R sub I. That's the dipole operator. So if I had, for example, a atomic gas with a bunch of atomic dipoles located at that position, each of them at a certain position R sub I, this would be, of course we could coarse grain it, make it a more continuum, etc. So this is QED. Quantum electrodynamics, but with a multiple expansion of the current. Now, what do we mean by a classical current? What we mean by a classical current is that the quantum fluctuations associated with the current are negligible, and that we can replace this by its mean field, its mean value. So classical current, and in this case, classical dipole current or polarization current, would say we replace this by its expected value. Which I'll just call. So this becomes a classical field, not a quantum field. If that's a good approximation, then what is this Hamiltonian? So when we replace the current operator by its mean field, then in the dipole approximation, this is minus P dot E. Okay? And if we plug in our modal expansion for the electric field, then this takes the following form. It becomes the sum over all the modes, square root of some p, called p sub k star of t lambda a plus the Hermitian conjugate, where this is just the Fourier transform of whatever the classical current is doing. So the projection onto oh, I forgot my e to the minus I. Okay, t. Right, dot r. Okay, so it's the projection of that onto that mode, integrated over all space. Okay. Okie dokie. So, now, if this is my Hamiltonian, then if I start the field in the vacuum and I let the current do its job, what state of the field do I get at a later time? So if at t equals 0, the state of the field is the vacuum, then at a later time, if the state of the field is the time evolution operator acting on the vacuum, which is, because this commutes with itself at different times, I could just write at the integral of the interaction Hamiltonian in the interaction picture acting on the vacuum from 0 to t. And what is that? Well, that, my friends, is equal to the product over all the modes of the phase-space displacement operator for a particular displacement on the vacuum, where it's a little exercise to show that that alpha sub k is equal to the square root of 2 pi omega k over h bar v, the integral of this in other words, this is equal to so what is the point? The point is that when I had, because this thing was independent of the field itself, it evolved in some way driven by some other forces with some time. There was no kind of back reaction of this on this. This thing was linear in E. And because it was linear in E, it only had one power of A or maybe a power of A dagger. And that's what the Hamiltonian is. And when you exponentiate something with one power of A and A or A dagger, that's just a phase-based displacement. And the amount by which it displaces is exactly what you get from classical E&M. It's the amount of radiation. You may remember from E&M that the amount of radiation you get into a particular mode depends on the Fourier transform of the current. That's what's kind of coming out here. So this is just, what it's saying is that if I have a classical current, I get a classical field radiated plus the minimal uncertainty vacuum fluctuations. Okay? And I get a coherent. I will not get, if I have that kind of linear response, non-classical light. If I have a noisy current, where I have some classical statistical uncertainty on the current that's being driven, then that's a density matrix. Because I'd have to have a convex combination, a statistical mixture of different coherent states. And that's what's coming out of a light bulb. So in order for us to see something more interesting, we need to kind of go beyond this picture of the classical current. And we need somehow a current that depends itself on the quantum nature of the field, responds to the quantum nature of the field, so that we end up getting something nonlinear in E. And that will end up getting things like powers of A and A dagger, which, as we know, is what's important for squeezing. And that's what we're going to turn to next time. All right? Very good. And this is that state. So it's reduced uncertainty along the X quadrature and increased uncertainty along the P quadrature with respect to that theta. Okay? Obviously, there is a squeezed vacuum state of the kind I thought I drew, but it would have the squeezing parameter with a different phase. So that this squeezing parameter as written here, this is not a square, the square is supposed to be over there, is a complex number whose magnitude determines the amount of squeezing and whose phase determines the quadrature along which you are squeezed. And there's this factor of 2 that floats around over there. So it's half the argument of this, that is the quadrature along which you're squeezed. Okay? And this state is a minimum uncertainty state. Another important algebraic relationship is that this squeezing transformation, this unitary operator, induces a unitary transformation that's known as the Bogoliubov transformation. Okay? It kind of mixes together A and A dagger. So it's kind of like a rotation between A and A dagger by an imaginary angle. And there's an algebraic relation. You may remember there's this weird thing about Lorentz transformations and imaginary angles and their group relationships. So there is this kind of group theoretical relation. The last time we were talking about some of the algebra that we need to deal with in talking about this phenomenon of squeezing. And so the key operation we have is the unitary transformation that we call the squeezing operator. It has this form. Okay? Well, maybe get to today, if not next week, sort of where this comes from physically. Obviously, it involves something with pairs of photons, because it has A squares and A daggers, A dagger squares. And so we'll talk about that perhaps a little bit later in this lecture. So the state that one obtains, the state of of a single mode harmonic oscillator that is obtained by operating the ground state of the harmonic oscillator by the squeezing operator is what we call squeezed vacuum. Okay? And we draw it here in terms of the quadrature picture. It is a state that has zero mean amplitude, and it has fluctuations along the different quadratures that are anisotropic, that are squeezed along one of the quadratures. Actually, this is drawn backwards. Sorry. It's supposed to, let me try that again. So here's the X quadrature associated with that, and this is the P quadrature. Relationship between the Lyubov transformations and the group SU11, if you care. So anyway, but the idea here is that this Lyubov transformation, because of this mixing between A and A dagger, what it does is it rescales X and P along some direction, okay, associated with that squeezing parameter space. Furthermore, what we saw last time was that one way to understand where the squeezing was coming from was the fact that there is a coherent superposition of the vacuum state with the state that has a pair of photons in it, 2 photons in it. And the phase of this complex amplitude determines the quadrature along which I'm squeezed, where I get destructive interference versus constructive interference. Okay? So something which we say, is kind of related to the continuous variable reduction of some quantum uncertainty, it has to do with this kind of coherence between different numbers of photons. And in this case, it's between something with 2 photons and something with the vacuum. Okay? And generally speaking, this state has only even numbers of photons in it. You can kind of see that because if you were to act this operator on the vacuum, expand it out, it only has even powers of A dagger in them. And one of your homework problems is to derive this, or something close to it. All right? Right. One last thing about this that I think I failed to mention last lecture is that we can define for example, not just a squeezed vacuum, but we could have a squeezed coherent state with some mean amplitude alpha and some squeezing that need not be squeezed along the same direction as this phase. So it could have, some arbitrary kind of picture like this. Okay, so this is what we call a squeezed coherent state, and it's specified by the mean field and the squeezing amount. And it's just obtained by displacing through the phase-based displacement operator that we have discussed, the squeezed vacuum. Yeah?
Does it make any difference which way around you do
It does. That's exactly what I was about to say. This is not the same thing as they don't commute. You find a different amount of squeezing in this case. And this is the way that, to me, it makes sense in most sort of modern texts define squeeze coherent states, or this way. There was originally defined, there was a kind of debate at like what's the, at the, 20 years ago or more, how to do it, but we're not, these aren't equal, so this is, because this has the same amount of squeezing as the vacuum, squeeze vacuum would have had. It makes more sense to me to define it that way.
Do you,
Yeah.
if you do it the other way, do you still get a squeeze coherent state?
You do.
Okay.
But the amount of, what you're doing is you're squeezing also the X and P, so you'll change.
Yeah.
What you'll do is you'll shrink and increase your coherent amplitude. So
Okay.
your coherence that you get is not that alpha. You'll have a different alpha. You see that? Because you're going to end up de-amplifying and amplifying it. So it is a squeeze coherent state, but with a different alpha. So why would we do it that way? All right. Now, what we were talking about at the end of the lecture was the way in which one detects a squeeze state, and that will sort of lead us into the question of what the heck is a squeeze state good for? So we were talking about, in order to detect a squeezed state, we need to somehow measure in some phase-dependent way what these fluctuations are, because they vary as a function of the phase. So we need some kind of phase-sensitive detection. Now, one thing we discussed that, just to remind you, we talked about this notion of shot noise. Right? So if I have a photodetector, and it's an ideal photodetector, which has perfect quantum efficiency, that's the jargon for saying that every photon that comes in is converted to